So next we're going to work our way through a handout that's available as a PDF on Canvas, a handout on reference angles. So we have to define what reference angles are, and we're going to discover that as we work through this handout. It's a little bit subtle, so you may have to be patient with it for a little bit, and I think it will all come together by the end. So on the handout I say, we can use what we know about acute angles, angles between 0 and 90 degrees, to tell us a lot about the values of the trigonometric functions for angles greater than 90 degrees and also angles with negative measure. The key is to understand how angles with terminal sides in quadrants 2, 3, and 4 can have trig values that are related to certain acute angles that have terminal sides in quadrant 1. So we're going to look for symmetry in these following pictures. So first we're going to look at a particular acute angle in standard position that I call theta 1, whose terminal side intersects the point 5, 2. The diagram includes a circle centered at the origin that passes through 5, 2. What is the radius of this circle? And I blew the picture up a little bit here so it's a little bit easier to look at. Now, we can get the radius of this circle by taking the general form of the equation of that circle, x squared plus y squared equals r squared, and plugging in the coordinates of this point, 5 squared plus 2 squared equals r squared. Because that point would satisfy the equation, we get 25 plus 4 is r squared, so 29 is r squared. And when we take square roots, we get r, and now r has to be positive. So there's our radius of this circle. It's the square root of 29. What are the values of sine of theta 1 and cosine of theta 1 and tangent of theta 1? So I'm going to make use of our new formulas for sine, cosine, tangent that involve r. So sine of theta 1 is y over r, which is the y coordinate of the point 2 over the square root of 29. Cosine of theta 1 is x over r, which is the x coordinate of that point, 5 over the radius, square root of 29. And tangent of theta 1 is y over x, which is the y coordinate of the point 2 over the x coordinate 5. 2/5 is tangent of theta 1. So there we got our sine, cosine, and tangent of theta 1. And then on the handout, near the bottom, I say notice that since theta 1 is an acute angle, we can draw a right triangle with legs 5 and 2 and a hypotenuse square root of 29. And so we just note in this picture this right triangle has this length is 5, that side is 2, the hypotenuse is square root of 29, and that takes us back to SOHCAHTOA. Now we're going to leave SOHCAHTOA behind, but for acute angles, for angles in the first quadrant, SOHCAHTOA still applies. Now let's go to the second page of the handout. Now we're going to look at a different angle called theta 2, whose terminal side passes through a point with the same y coordinate but opposite x coordinate. And this point lies on the same circle as in the previous picture, right? If I take negative 5 squared plus 2 squared, I'm going to get positive 29 is r squared. So it's on that same circle. And here, again, theta 2 is this angle here. It's not an angle in a right triangle, but we can calculate sine of theta 2, cosine of theta 2, and tangent of theta 2 using our formulas, our y over r formula. So r is still square root of 29, and y over r is 2 over the square root of 29. Cosine theta 2 is x over r, which is negative 5 over the square root of 29. So it's negative, and tangent of theta 2 is y over x, which is 2 over negative 5, or negative 2/5. And I guess where this is going is we're going to notice that the values for theta 1 and the values for theta 2 are similar. Sometimes they're equal, but sometimes they're opposites. Sometimes we get a negative, and we're kind of trying to decide this equal opposite relationship between them. Now, down at the bottom of the second page, I say just notice that the trig function values for theta 2 are similar to the values for theta 1. And I want you to look at a certain triangle in this picture. Now, the right triangle is shaded, and it does not include angle theta 2. So we were interested in the trig function values for theta 2. But in that picture at the bottom of the page, the right triangle is actually outside or separate from that angle theta 2. However, when I draw a triangle in this position, this angle that's marked in the corner is equal to angle theta 1. In fact, this triangle is exactly congruent, just in a slightly different position, from the triangle in the first page. So there's a triangle here. It doesn't include angle theta 2, but it's weird that it is congruent to the triangle on the first page. That's the only observation we want to make from this picture at the bottom of the second page. Now let's move on to the third page. We're going to move into quadrant 3, and we're going to look at another angle, theta 3, with terminal side passing through the point -5, -2. Here's a blown up version of the picture. Now that point again lies on the same circle, because if you take the sum of the squares of those two coordinates, you're going to get 29. So its radius is still square root of 29. And so what are the values of sine theta 3, cosine theta 3, and tangent theta 3? Well, we're still doing y over r. So again, r is still same square root of 29, but it's the positive and negativeness of these coordinates that are determining whether the sine and cosine tangent are positive or negative, right? So for theta 3, y is -2. The radius is square root of 29, so we get a negative sine value. Cosine theta 3 is x over r. X is -5 over radius square root of 29. We get both a negative sine and cosine value. And tangent of theta 3 is y over x -2 over -5. So a negative over a negative is positive. Tangent actually comes out to be positive. This is kind of reflecting what we discussed in the previous video, where in the third quadrant, only the tangent is positive of these three functions. And yet the values are related to the theta 1 values. We're just getting some of them negative. Now, if I take this picture of angle theta 3, theta 3 is an angle greater than 180 degrees, right? We can draw a right triangle in that picture that does not include angle theta 3, but is as shaded. And this is a blown up picture of the circle at the bottom of the page. And this is another triangle that's congruent to the triangle from page 1 and the triangle from page 2. And there's actually a little copy of angle theta 1 right in this corner. So it's not in standard position, but there's some symmetry going on here that we're going to work with before we're through. So we just want to make that observation from page 3 and go on to page 4. We're going to look at one more angle. And you may probably guess where I'm headed here. I'm going into quadrant 4, and so I'm calling this angle theta 4. Let's blow up the picture. So angle theta 4 is pretty big, almost a full circle angle here. And we have our formulas for calculating the sine, cosine, and tangent of theta 4. And sine is y over r. Radius, again, is square root of 29. Even though x is positive, y is negative, the coordinates of this point satisfy that same circle equation. And so y is negative 2 over radius square root of 29. So sine of theta 4 is negative. Cosine of theta 4, x over r, is 5 over the square root of 29. So cosine is positive. Tangent of theta 4 is y over x. That's going to be negative 2 over 5. And that ends up being negative. So here the sine and tangent are both negative. Cosine is positive. We're in quadrant 4. And yet the values, if you don't pay attention to which are positive and negative, look very similar to the theta 1 values. Now theta 4 is not theta 1, but if we go to the picture at the bottom of the page, we can again imagine a copy of that right triangle related to what's going on here, even though it's, again, it does not include angle theta 4. In fact, that's a little copy of angle theta 1. The shaded triangle here is congruent to all the shaded triangles we've seen along the way so far. Now let's go to the next page. So we kind of got this, I've gone back to, I've drawn this bow tie picture, I call it, with all 4 shaded triangles included, can help us see the symmetry of the terminal sides and what are called the reference angles. So what we're going to say is we're going to say theta 1 is the reference angle for theta 1, theta 2, theta 3, and theta 4 on this handout. So all 4 of those angles have what's called the reference angle of theta 1. Notice that in this picture, I notice how I added a rectangle here on the inside. That just sort of highlights the point that as I go across, the y coordinates are the same, positive 2 along the top, negative 2 at the bottom. On the right side and the left side, the x coordinates are the same, right? I have a positive 5 x coordinate on the right, negative 5 x coordinate on the left. And I'm going to use this bow tie picture in some of the exercises that follow. So right now, we're just sort of observing this, and we'll work with it in a minute. And let's just read this statement. Okay, I lost my, in summary. The positive acute angle, usually not in standard position, formed by the terminal side of an angle theta in the x-axis when theta is in standard position is called the reference angle for theta. Now I know that's quite a mouthful, but for theta 4, we're going to call this theta 1 the reference angle for theta 4. When we go back to theta 3, this theta 1 copy is the reference angle for theta 3. When we go back to theta 2, this copy of theta 1 is the reference angle for theta 2. And we'll even say that for theta 1, it's its own reference angle. Now, we're going to start doing the exercises in a separate video.